Hello and welcome to Calculus Tutorial. We are continuing our look at limits and the actual limit definition. We sort of got a conceptual idea last time. Now we're going to actually take a look at the hard algebra with how that works. So here is our definition again. If you have a limit, what that means is that for every epsilon there is a delta. And we did that by guess and check. I gave you an epsilon, and you guessed and checked the delta. We're not going to guess and check anymore. We're actually going to use this algebraic statement down here to figure out how far away you can be, still staying in the boundary of your epsilon. So you have to think of delta as a distance. How far away from x can you be? Well, distance is simply subtraction. How far away from x can you be? And you subtract it. Okay. How far away from the limit are you allowed to be? Well, distance is again subtraction. So you have your y value and your limit. So how far away from the limit can you go? If you subtract those two, that is your distance, and that has to be smaller than epsilon. It needs to have an absolute value because when you go above, you are going to have positive, but then when you go below, you're negative. And so you take the absolute value to keep things positive. It just helps out. So let's take a look at how that works for an actual example. We're going to do a linear one first. Those are the most simple. Okay, so I'm going to start with those two statements one more time. So we have our nice limit here. Actually, let's figure out what this limit is. No funny business here, so we can just plug in 6. 6 times 1/3 is 2, minus 4 is negative 2. But if that limit is true, for every epsilon, there must be a delta. And so the absolute value of x minus c will be less than delta. And the absolute value of f of x minus L is less than epsilon. Okay? This is the distance away from x. This is the distance away from y. So we're going to work on this side because we can actually do some things. We know what the limit is. The limit is negative 2. So we're going to have minus a negative 2, which becomes plus 2. We can also plug in f of x. F of x is our function right here. And so what we're going to do is we're going to plug in the function right here. 1/3 x minus 4. So what does that give us? If we simplify that, that is still less than epsilon. We get 1/3 x minus 2. Absolute value is less than epsilon. And over here, we can do a little bit of work as well. X is going to stay x, but we know what c is. C is 6. Okay? So what we need to do now is find a way to take these two equations and combine them, because I need a relationship between delta and epsilon, because for every epsilon there is a delta, so there must be a relationship. And so we have to do a little fancy algebra over here. What I'm going to do is factor out 1/3. There is still an absolute value here. But what do I get when I factor out 1/3? Well, that's just going to be an x. What does this number become? It actually becomes a 6. Double check that. If I distribute 1/3 times 6 is 2. So that does work. Is less than epsilon. Some of this algebra you might be able to do in your head, but that 1/3 can come to the outside of the absolute value because it's positive. Now, what we can recognize right here is the same as over here. So what we're going to do, yes, I know there isn't an equal sign here right now, but think of this as the same thing as delta. So I'm going to replace this with the delta. So we're going to get 1/3 delta is less than epsilon. And then I think I'll multiply by 3 so that delta must be less than 1/3, multiply by 3, 3 epsilon. Now I have related delta and epsilon. We now have a relationship. We have proved that this limit does in fact work. If the absolute value things, the inequality signs and my substitution is bothering you, come talk to me. I can give you a longer explanation as to why that actually does work. All right, so we've got one example with linear. Let's try a harder one. Oops, yeah, that's what I want. So we got our linear example. Let's do a quadratic example. So here's our function, x squared plus 5x. Prove that the limit as x approaches 3 actually equals 24. Hopefully you can see if you plug in 3, 9 plus 15 does give us 24. But prove that the limit exists by determining a delta for any epsilon, which means I need an equation that relates delta and epsilon. So we start with what must be true for the x's, must be less than delta, and then for the y's, so make sure you think f of x is y, minus the limit, which is a y value, is less than epsilon. And we just start plugging everything in at first. Over here, that will be x minus 3. And over here, f of x is x squared plus 5x. And the limit is negative 24. Well, sorry, yeah. So it's going to be minus 24. And that needs to be less than epsilon. So what can we do here? Hopefully you can see that we can, in fact, factor this. So what numbers multiply to be negative 24 and add to be positive 5? X plus 8, x minus 3. All right, so this here, just like last time, is the same as this over here. And so that is going to become delta. And yes, we still have our absolute values here, is less than epsilon. And so what we're going to do is divide both sides by x plus 8, divide by x plus 8. And so delta has to be less than epsilon over x plus 8. All right, now I got rid of the absolute value because the definition says delta always has to be positive. It's a distance, and so I don't really need those anymore now that delta is the only thing left. But this is a little unsatisfying because we have an x plus 8 down here. I'm supposed to relate only delta and epsilon, not delta, epsilon, and x. So what we're going to do is a little bit of logic, okay? The smaller delta is, the better. If you get really, really close, you're going to be much more accurate. So we want to make this smaller. How do I make this smaller? you make the denominator bigger. And so think about, what is x going to be? Well, x is going to be very, very close to 3. But I want to make sure I'm safe here. So I'm going to pick a number that makes the denominator bigger. So I'm going to be close to 3, true, but I want to make this denominator bigger. So what is a kind of a ridiculous number that's far away from 3 that makes the denominator bigger? So I'm going to go 3.1, 3.2, 3.5. What's a ridiculous number? So think about all the numbers you typed into the table when we guessed and checked. All right, you would get really, really close to 3, 3.01, 3.001. You're really close. Go ridiculously far. 4. You would never type in 4 into that table. It's way too far away from 3. You want 3.01 usually. So we're going to put in 4 in for x. That will make the denominator bigger and therefore make delta smaller, which means I'm pretty safe that it will always work. And if that's a 4, 4 plus 8 is 12. Okay, so there's a relationship that will always work. Will it hit it exactly? No, and we don't need to hit it exactly. We just have to make sure that we're always safe. As you can see, there is no equal sign here. There's no equal sign. As long as we are guaranteeing that we are always less. We don't have to hit it exactly. And so that 12 down there will make sure we're always less. Now, if you wanted to be a little ridiculous, could you have made something bigger than 4 and said 10? Well, yeah, 18 would make you even more accurate. Could you put 100 down there? Well, yeah, 108 would make you even more accurate. A little ridiculously accurate. And so we're trying to get to the equal as close as we can without being in danger of messing up this inequality. So epsilon over 12 is a good compromise, I would say. All right, so we have proven that this limit does in fact exist. So let's talk about the point of this all, because that limit was extremely easy. Why are we trying to prove that it exists? It's important to know that it does. So what is our conceptual takeaway here? Well, what we have been doing with limits so far is we have been showing that it is possible, with a right epsilon, we can shrink this distance down, and that limit does in fact exist. And it always shrinks down to that point. Whether that point is actually there or not, when you get closer and closer to it, they converge. Now, why is that important to calculus? Well, we're going to do that same thing, but with slopes. And we actually did this the first week of school. If I want the slope at one point, I first take the slope between 2 points. And then I take this delta x, the distance here, and we shrink it down until we get the slope at 1 point. We get the tangent line. Now here's the problem. Watch what happens. If I actually do the slope at 1 point, it disappears because the slope is delta y over delta x. Can delta x actually be 0? No. If you make delta x 0, you're dividing by 0, and that is not allowed. And so what we are eventually going to do is we're going to take the limit as delta x approaches 0 of delta y over delta x. And that is how we really start defining the derivative, the slope at 1 point, because we have that dividing by 0 problem. Now, it'll take a few days for us to get to because we still have more limits to do, but that is sort of the significance of all this, is getting rid of this divided by 0 problem. All right, hopefully that clears some things up for us for limits.